All right. It's
We're
Friday
live.
in the internet work. Oh my goodness, we're live.
We're live.
Hey Ben, how are you?
Uh
I
I
heard
you
that.
know that happy tired when you've been up late at night trying to fool around with something because you just can't stop.
Right, I was 17 at the time, but yeah.
I still occasionally do that, and I'll probably pay for it tomorrow. But today I'm just pumped up, full of caffeine and other things that are totally legal and okay because I have ADHD and I have an actual psychiatrist who decided I should try Adderall, and it does help a bit.
Oh, cool.
But I was here in my office till 3 a.m. fooling around with this thing. This is really, really cool. This is
Oh, what is this?
this friends is the RTP scope, and I want to say thanks especially to Rhodey and Schwartz. But this is a loaner. Again, much like a few months ago, we had the amazing Keysight MXO, or was that MXA?
Right.
I forgot which one it was. But this is Rhodey's flagship scope. If you go to their website, this is the RTP 164B.
Right.
And the 164B is the top of the line on the website. Any higher than this is going to be a custom build. Right. But this thing is absolutely beautiful. But the software
it's got
in it
its
is
own zip code, right?
pretty much. And this is a demo unit, so I will be sending it back to them at some point. But for now, I'm going to have fun with it and make some videos with it. I'm going to use it. Some of you might know or might not. I'm doing some cool playing with some of the brand new, just hitting the market IMX processors from NXP. I keep saying Freescale, but it is the Freescale group that is now part of NXP based in Austin, Texas, and they do the IMX processors, which are just really, really powerful. This particular one, the IMX 93, is actually very powerful processor, but very low power. And there's an even more powerful one with 3D GPU, but also targeted at like wearables and that kind of thing, where you need cool graphics and human machine interfaces, but you need very low power because you're going to be maybe running off a battery or something. That's the IMX 8 ULP. And so while I'm working on that, some of the stuff I want to talk about is hardware design and how to do some of the high-speed interfaces. You'll see, this has DDR4, low power DDR4. It's got LVDS and MIPI and gigabit Ethernet ports and USB. This one doesn't. The IMX 93 doesn't have USB 3.0. It's USB 2 still. The 8 ULP. And the next IMX 93 part that hasn't come out of fab yet, but they're just about to release it, has USB 3.0. But if you're designing with any of those, you need a scope that can tell you if your signal integrity is good or not. So, and this is cool. Like, this is just running an RF demo right now. So I have my capture device plugged into the back of the scope. There's a display port. Let's go solo on that. And this is just one of the cool little demos built into the software of the demo unit that just does an RF, frequency sweep of a sine wave, and you can see that in the spectrogram, the spectrum, and the actual signal in the top trace there. But just this is cool. The software in this thing is really very easy to navigate. But if I go back to desktop here, you see it's running Windows 10. And the nice thing with Rhodey is that on this unit, they've given it to me with the default user being a local administrator, so I can install other software on this. Now, there's not a ton of hard disk space on this thing, but there's enough. Like if I want to make videos with it, I can put Camtasia or other screen capture software directly on it, and it's pretty capable machine. If we look at the specs. It's an AMD, I think. Let's see what's in here. Yeah, it's got a 240 gig SSD. It's a AMD processor, AMD Ryzen with built-in Vega graphics, 16 gigs of RAM, running Windows 10 64. So that's all pretty cool, but the actual roadie software that's running on this is just superb. It is superb. Like, if I want to look at different apps, we can. I'll just show you a quick demo here. Let's go to protocol. So there's all these different protocol analysis options. So Bill, you were working on USB 3, a USB 3 product. Now, I don't have the cabling to actually do this, but we could do USB 3.1.
I'm back.
Oh, you disappeared?
Oh, wait. Can't hear you.
I can hear you. You're here.
And now I should be back.
Hello, Bill. You were back.
There we are.
We can hear you.
My computer just shut off all by itself, and now monitors are dark and stuff. So I think I had a hardware problem.
Oh, well, you're with us, and it's okay. I was just gas bagging the whole time about.
Yeah, go. I've done that.
So yeah, I mean, USB 3.1 super speed, USB 3.1 super speed plus, and this is like you could have used this last month. The USB power delivery, it does protocol.
Right.
Like it'll show you the handshaking, PCI, MIPI interfaces. So all this is very cool. Manchester encoding, decoding, 8B, 10B. I'm going to just pick 8B, 10B because that's the most sort of generic. So what's actually happening here is it's the cool thing about the demo mode here is it's not just playing back things that they've previously recorded and showing it to you on the display as if it's real. I got the cabling kit for 2 channels. So I have some pretty high-end SMA cables, and with the SMA, high bandwidth SMA to BNC adapters here. And this scope, I wish I could get the webcam working on my other phone here because I wanted to show you what's on the front panel. Let me, yeah, I'll just point at it so you can see it from here. So there's optional modules here. This top module is the pulse source modules. It's got a couple of reference ports and a couple of output ports, SMA. And some of the demos use that, and some of the modes you can use that as the pulse source is a high bandwidth signal generator. Basically, you have as close to a perfect pulse as you can generate that has a very high frequency content.
Wow. Oh, so you can do TDR with this.
So yes, so this will be used as an impulse generator, and then it can do the impulse response throughout whatever the network is. So here I've got this is just an FR4 board I made some years ago for an RF and microwave board design class I put together, and this one happens to have a bandpass distributed element bandpass filter on it.
All right.
I've shown this probably on our stream before, and so I can pulse through that, and so yes, this is a scope, but because it's so high bandwidth, it's 40 gigasamples a second, 16 gigahertz bandwidth. So with the right software running on it, there's spectrum analysis, and there's all the math stuff, the math menus, and there's protocol analysis. So that means I can test some RF structures as well. So that's the other thing I'll be using this for. But underneath that, the second module is a 2-port generator module. And it has a little pattern generator, digital pattern generator board that can plug into that. I haven't done anything with that yet. I'll come around to that. But then there's 2 other BNC outputs that'll do, it says it's 50 ohms. It'll do up to 6 volts peak to peak. And depending on the mode. So like currently that's actually the pulse. Which one is it for this demo? Is that C3 that was coming in on? Anyway, this 8B, 10B coding came out of the pulse source for this recording. This is a recording that I triggered last night. But then the other demo mode that we were looking at when we started with that RF source, that was doing the sweep out of this lower module here, the generator module. And we can do something like, there's a whole lot of different options here. We were just looking at the spectrogram one. Look at this IQ. So
wow, yep.
So this is gonna, so input sample rate 20 gigasamples a second. So this is going to capture pre-recorded. This is a pre-recorded waveform. So this is an arbitrary function generator, and the pre-recorded waveform has been modulated, right? So where do we want to go? I guess we can, it can actually generate this. So carrier frequency, we can adjust all this stuff for the demo mode. Record length, sample rate. Okay, it says on. Where's the go button though?
So can I ask you questions while you're doing that, or is this?
You can. I probably won't be able to answer them because I'm just new at this.
Just how low does the spectrum analyzer go in frequency? Down near 0, or is it like a 9 kilohertz thing?
Now I was talking to someone at IMS just 2 days ago. I was at the International Microwave Symposium in San Diego. It's
Okay.
kind of the big trade show each year for RF and microwave engineers. And the roadie booth, one of the FAEs, super nice chap, I've forgotten his name, was explaining this to me with one of their VNAs, that they do actually go down to DC, but there's some software tricks they have to pull to make it happen.
Okay.
But they have a special algorithm. Yeah. So,
all right. Well, there's your answer, Karsar.
yeah.
So how fast do you reckon the rise time is on the pulse generator?
Less than a nanosecond. Yeah. So back to what have we got in analysis then? Just do advanced I. So this is telling me, okay, to run this demo, I need to hook up the cable between channel 1.
Oh, that's cool. And
the B6 module, which is that lower module, Gen 1 output. Right. So it's not just, like I said before, well, that's what I like about some of the demo apps in here. It's they're actually generating the real signal and running through the actual process, like with a script.
Right.
Versus just giving you a screenshot that they captured in the factory sometime previously, you know?
Right.
What's going on there? What is that? Yeah, that's better. So it's actually, yeah, running through a script. Now, I don't know what kind of SDK they have on this, but I'm pretty sure It definitely supports all the industry standard protocols because it's got the
I saw that.
got the port on the back. It's got the IEC 525 SCPI port and all that stuff. Right, so it's generating this pulse signal now.
Does it make coffee? And if so, can you set the temperature of the coffee?
I think that's an extra hardware plugin, but you could certainly do that.
They don't do it in software yet.
Right,
okay,
so
we got pulses.
This is using the arbitrary waveform generator down here to actually play back PRBS.
Right.
With some clock embedded in it.
Right.
And so then it's just explaining what happens at each step and, where you would go.
That is cool. So it does the clock de-embedding for you. And I didn't see you do a lot of things to make this happen. I mean,
I just hit next.
Made it look easy. Yeah.
Yeah. And then the next step is you can add the mask test to it.
Right.
So it gives you that MT1 in the middle there. That's your
window.
That's your mask. And I could just let this carry on running. And that's all cool and everything, but I'm going through their near perfect SMA cables, like the cables that came with this scope kit and all the little SMA adapters. They're all the highest quality you can get. So, just the cables alone are probably a couple of $1,000s each normally. So the next thing would be, okay, well, let me put my cheap, crappy SMA cables and see what it looks like then, right? So,
can you store this waveform also? Not to derail what you're doing, but that's another thing you can, if you pop it into a register.
Yeah. Now from here, where would I go to do that? Let's close that. So I could do save.
And this program's from Rode and Schwartz that we see here. This is a client.
When you say client, what do you mean?
It's the screen that we're broadcasting. Is that running on a? That's running on a PC. That's not just VNC to the device, right?
Well, the device itself is a PC. So the scope is running Windows 10, and it's got a display port output on the back, and I'm capturing that, and that is what we're looking
you're capturing it in hardware. That's right. You did say that. Okay. So to answer the question in the chat, this is the software that runs on the oscilloscope itself. We're just capturing it on HDMI or display port.
Right. But there's other ways you can remote
desktop. Yeah, there absolutely is. Yeah. You can screen share on a lot of them with BNC.
I'll show you another one too. Like this scope, like most good scopes will have this nowadays, but let me open up a browser window. Give me 1 second here. Yeah, so this scope is on my network, and it's just, I'll put this on my other display. So I'm running, let me do share screen, and I'm going to screen 1. Right, so this is Edge browser on my other display, and I can go to the scope, which is, no, I don't want Bing search.
Yeah. So you are running a web browser on your scope.
Well, it's got a web server on it. So this is the scope I'm accessing through a web browser.
Oh, I gotcha. Yeah.
Right. So, so this is the scope details. I can see its address on my office network. It's the Visa. So if I was going to access this with Visa, that's a protocol come up with by National Instruments.
Yeah.
I could access it through those. So if I'm running any scripts on another computer or server on the network for automation of any kind. But it's also got this web control. So basically it gives you the same user interface through the browser. It's kind of like using Citrix or something like that, right?
Right.
But it's a bit clunky and slow. Anything done through a web browser is going to be a bit slower. I'd rather just RTP, like remote desktop, or I could use VNC. You could install VNC on it. So, but yeah, I mean, you kind of this is the basic features you'd expect any decent scope to have now anyway, really. I mean, so even the cheaper scopes, they don't necessarily have the web server thing going on because they don't have powerful enough CPUs to run Windows or anything. They're just probably some kind of ARM APU running a custom OS or some variant of FreeRTOS and their own software.
Right.
But you can, at the very least, connect to them and control them over Ethernet now.
Right.
So,
right.
Which is the one? This is the I don't want that on there anymore. Let's go back to the real deal. Yeah. So, I'll close that web browser too because it's extra load on the scope CPU. I don't need to give it. Even though I'm sure it's quite capable. So you can see I can save anything from screenshots to histogram data to reports. And again, like I'm just barely scratching the surface. I've only just received this thing and had less than an hour with it. Well, no, that's not true. I was playing with it for a few hours last night, but less than a solid hour. But you can see like everything you need is that you can save waveform data. You save a whole set of everything. But I think the real value there is setting it up to do something over a long period of time. So like what we're looking at, particularly when it comes to signal integrity analysis, right?
Right.
So what we're looking at here is a close to perfect output from the gen through a close to perfect cable. So I could run this literally for a week and it'll do, millions of slices and it'll have a 0% failure rate and 100% pass rate. The real value is those buttons. The real value would be to pump this set this up, but then pump the same thing through my own hardware.
Does it have any BERT analysis built into it or BERT generation, bit error rate?
Yeah, well, it does, but that's essentially what we're looking at here with this
right.
Little,
so can you
report.
inject BERT into it?
I should be able to. Let me see if I go to the generator.
Right.
And this is currently a pulse source. Wonder if I can change this. It's free running. See, I think because it's currently under a script, it's so again, showing my ineptitude by asking tough questions, Bill.
Oh yeah, I knew I was asking a tough one. I apologize,
but this is okay. So this is the other really neat thing. This thing has all this cool embedding, right? So
right.
So right, it's got all these.
So de-embedding. Tell us about de-embedding.
So the problem is once you get, beyond a certain frequency band or whatever, once you get to a high enough bit rate, or if you're talking RF, once you get to a high enough bandwidth,
right,
then every little piece of metal and plastic in the whole setup affects the signal and what you're seeing. So it's very hard to distinguish between what's the device you're looking at and what's the cabling and other stuff around it. So de-embedding is the process of measuring all of the test jig first,
right,
and then measuring it with your device under test, and then subtracting the test jig from it. That's the simplistic way of doing it, but there's all sorts of algorithms for doing that. So now when you do it, Bill, and you've got your you've got your communications, your CSA 803, right?
Right.
And you're using it as a TDR. So the way we used to have to do it was you'd measure a device just using a TDR. So you send a pulse, a step response, down your test cable into the device under test, and then you're measuring at the beginning of that reflections or whatever. And so you know the length of things and you see the TDR signal on the scope, you capture it and you see, oh, well, there's this noise here. Well, that's the connector on the front. And then there's this, it goes along, and then there's this other little blip here, and that's a adapter or something to my board and the connector. And then so everything before that, we basically don't look at. And from this section onwards, we see the impedance, going up and down. And now we know we're looking at structures on the printed circuit board and pins on chips and whatnot. And so you manually de-embed just by knowing what to ignore in the signal waveform you capture and what to look at. But it's not always so easy to do that. And sometimes you want spectral content rather than time-based content.
Right.
And it's not so easy just to do that, right? So these high-end scopes have very fancy algorithms for. They know this their own probes and leads and things. So let's actually go back there, and I'll do this one because this is another type of kind of de-embedding, right? Where we want to set up a proven cable, right?
Okay.
So we're going to normalize this, and it tells me, okay, on the pulse module, what we're going to do is take our two high-end cables. One of them's going to go into channel 1, and that's our reference, right? So I'm going to disconnect that from the generator output here. I should really have my SMA torque wrench.
Yeah, I got a couple of those.
That goes into the first output on the pulse source module. I'll go and grab my torque wrench in a sec. It's just around the corner, right? And the out bar. It's hard to see on the video here, but on the screen, if you look in the center there's two outputs. There's a true and a complement. So it's basically a differential pulse source.
Right.
And so the out bar, which is the negative going, or complement, is going to channel 3. So I have to.
So you mentioned SMA torque wrench. Here's mine. A little. It's like a big torque wrench. Is only it's set for what, 5 pounds for SMA, something like that,
or even 4. Because SMA
ounces,
they can actually be. It seems like the better quality they are for signals, the more fragile they are mechanically.
Yeah.
And the more mechanically tough they are, the crappier they are for signals, like for maintaining impedance and bandwidth. Right. So I'll go get mine. 1 second. Entertain people while I'm gone.
All right. So we're here on the third green. Ben is laying a hard birdie. He needs to make this putt, or we're going to.
That's so funny because golf is ridiculous. Got to be the hardest game ever invented, and I am not good at it. So this one's only set to 4-inch ounces. Even just finger tighten, it's already tight enough, according to this torque wrench.
Right.
And there's a couple of, I think, precision 50 ohm terminators on these other reference outputs that had to be attached as well. Yeah, so these are already tight enough, according to this torque wrench, which is not a super expensive one, but okay, back
here we see the native engineer in his home environment playing with an oscilloscope. He doesn't notice our approach as we approach carefully through the weeds. Engineers are easily startled when in this state of contemplation.
Yeah, this is when you have your buddy come up behind you and pop a big paper bag, or I had a friend do that to me. I was actually working in something. I don't even remember what it was, but I was poking around and I was near the power supply.
And somebody did something?
He was right up close behind me and he just went, bang!
Right. Creates voltage.
About jumped out of my freaking skin.
So it's in my book, but somebody got up behind me in the old days at Commodore and did that. And I'll just say they never did it again.
No, they probably had a bloody nose.
His little feet couldn't touch the floor. I was holding him up against the wall. Yeah, looking at the second guy. I didn't know if I was going to swing on him too.
Okay, this says measurement failed. Check my setup. So the first channel is going to channel 1. Second one's going to channel 2. Channel 3. And in this case, it's C3, channel 3.
Okay.
Is called device because the idea is, okay, so what we do is we're doing this to normalize or de-embed the cables. But then we're going to do a measurement that compares the reference, which is channel 1,
right,
with whatever else we add to the connection on channel 3. I did this last night and it worked just fine.
And de-embedding can actually be done with regular old matrix math, if I remember right. It doesn't need like a transform to FFT or something.
Yeah, because if you think about what it actually is, okay, so that worked. Yeah, if you think about what it is, it's just it's like it's a cancellation process. So it's a subtraction of something.
Yeah.
But it's a subtraction over
time domain
or over time. Yeah. Okay, so what we're looking at here, this is the result. This is basically
cool.
The reference insertion loss of these high bandwidth cables. So you
is
can
that
see
15 gig, that corner?
Yes, and they need to go up high because it's a 16 gigahertz bandwidth scope, right?
Right.
So I can assure you, none of the test leads hanging from my workbench will have this kind of bandwidth.
Hang on, let me see what my best cable is. Hold on.
So that what we just captured of the test setup,
Right.
right? So there's a slightly bigger picture, but I've saved that saves it to an XML file, so I can recall that later. And if I reuse the same cables in the same positions for a test setup later on, like that's the cool thing. Like once you de-embed a particular jig, you can keep that. You can keep that setting. You save it and reuse it.
Right.
It tends to be pretty stable. So
isn't part of characterization, from what I've seen from looking in the EMI kind of or SI type of magazines, is how careful you are about the cable dressing and the layout and the torquing and everything. Repeatability is the result of carefulness, is
yes,
what it looks like to me.
I'd say that's true. And so, for example, the sales of these little SMA torque wrenches, whoever makes them and sells them, they've got Eric Bogerton to thank for it, because he's one of the folks that really demonstrates that stuff all matters.
Right.
In a lot of the classes I've seen him do at DesignCon and other places. So
what do you suppose it is? Is it contact? Is it deformation of the connector when you torque it, or is it purely about contact pressure on the contacts?
that's a good question. Because if you think about it, to make a proper connection, the pin has it's in the metallurgy, I think. And I'm no expert. Yeah. I'm just guessing, but when you do this kind of thing, and I'm talking this up with the torque wrench, right? It's rubbing. Right. It's physically, and this is why these connectors, right? They don't last. You can only use them.
They don't. Right.
Because there's a thin gold plating surface, and I can only torque it so many times before that's worn through.
Right.
And you know, at those high frequencies, all the signal flows through the very thinnest outermost layer, because of the skin effect, right? So if you wear off the gold plating, then you're changing the impedance.
Right.
Of that structure. Okay, so I've introduced another cable segment here, right, which is one of the old SMA coax cables that actually came with this FPGA board that we talked about before we started streaming. So, folks, I'm still working on this. I couldn't get this to work today, but I have a Vertex 2 Pro card here that has the Rocket IOs. So these are 3.125 gigabit interface connections used for multi-gigabit Ethernet and stuff. This is a very old FPGA now, but I can use it. The goal was to use this as an external PRBS differential signal generator to do some comparisons. And I couldn't get the old Xilinx place and route tools to work. They don't like Windows 10. They worked fine last time I used them, but there's been updates since then, and it's frustrating as hell. So I've got to set up a virtual machining, and I just haven't had time to do that yet. Anyway, so what were we talking about? So getting back to...
We were de-embedding. You were going to use a poopy cable in the middle, I think, to show.
Yeah, I put the cable that came with that Xilinx daughter card, which may or may not be a good one. They were supposedly good back in the day, but they are quite old. It's like a 20-year-old cable now, so it's probably kind of crappy. But next step is we're just going to measure that. And so it's comparing the normalized cable, and you can see the actual pulse looks really good, but you can actually see the delay in it from the extra cable length. You see that delay right there?
Right. How long is the cable?
It's about 1.5 feet. So not super long,
Right.
but long enough to introduce delay and some additional loss.
Right.
So,
And it'd be about
look at that.
6 inches per nanosecond.
So this is with that cable added. And essentially what we're looking at here is a
notch filter.
It looks like a stub.
Yeah, a notch.
Right?
Yeah.
And it's like, it shouldn't look like that stub. because I have a series cable I've introduced, but isn't that interesting? Yet it's still pretty high bandwidth. It's good enough for the Xilinx Rocket IOs at 3.125 gigabits a second, because if you look, we've got pretty good bandwidth. Like the -3 dB point is up around 7.5 gigahertz.
Right.
So,
right. And it only goes down 20 dB. But yet that is weird. That's not loss. That's a notch. That's a stub, as you said.
It definitely looks to me like a stub because we've got less loss above it.
Right.
And that's kind of how you know. Like we're
right. It returned to normal at a higher frequency.
Right. So, but what do we have there? Well, we have a little SMA to SMA nipple in the middle to allow me to join the two cables end to end. But it should be like it came with the scope, so it's got to be a pretty high quality one, I would imagine. So I don't know. And we could look at it in the time domain and see at what length. See that we could do TDR. We should probably try that. Let's have a look.
Now, if you had this scope yourself in your own lab, based on what you said about the wear on the front panel connectors, would you tend to use a sacrificial double connector, you know, on your front panel, like a nipple? I mean, it'll degrade the signal, but it won't degrade the scope.
Yeah, I'd say it depends what I'm doing, but that's the cool thing. Like that's why we have de-embedding algorithms in these, because we can get rid of the effects of additional things like that, can't we? So yes, I would use a sacrificial adapter or cable wherever I could or where it made sense.
When you could and where you could, yeah.
Yeah, you use the high end ones that come with it for where you absolutely need the full bandwidth. If I'm connecting into an interposer probe for a DDR4 or 5 interface, it's going 3 or 4 mega transfers a second, and I want to look at the waveforms and make sure I've got good signal integrity on the board. Yeah, I'm going to use the good stuff.
Yeah.
And if I look closely at the cables that came with this and the BNC adapters for the front panel channels, they're all very high-end plated stainless. So they're extremely tough. Like they're built to last. But yes, at the same time, if I keep messing around with them, then over time they will degrade. But it'll take a long time. Again, this is very, very high quality stuff. Whereas these, who knows where these? Yes, the SMAs are gold plated, but you can bet the gold plating on these is not particularly thick, right?
They're gold colored. Let's say that.
And again, like when these came out with that FPGA board, that board and the cables that came with it were sold in a package, and it was $1,000. Like they weren't cheap at the time. I'm talking 20 years ago. So,
right.
What's that like now? Like $8,000 now? Anyway,
right.
But I don't know. I don't know who made them. I can't vouch for them. I can tell you this: the SMA connectors on this little board that I'd done for my RF and microwave PCB class.
Right.
As an example, I've put these boards together using decent Samtech connectors, which are rated for, I think, 26 gig. And that's what's on this one. And I've used the ones from AliExpress from China. And the first few times you play with them, if you just want to get a ballpark figure, the cheap ones work. They do work.
Right.
You would see them. You would definitely see them more on a TDR. You would see them. Right. But for looking at the RF bandwidth of a filter on a VNA, when I'm only using at the time I was only using a $500 USB VNA, and now I have a better one. It's the KC901V that is still a pretty cheap VNA. It's like $2,000 VNA. And for that, for getting your for getting your S parameters,
right,
they're okay, but they're not going to last. They fall apart in they're just, the metal in them is not high quality. It's because there's a bit of gold plating on them that they actually work. And eventually
1 micron gold plating. Yeah.
Yeah. And after so many talkings, they start to fall apart.
You knock the 6
metal
gold atoms off, and now there's no gold left.
Yeah. And they can totally disintegrate. So, it's RF connectors are a funny thing, because you can look at an SMA, and the best ones don't solder. The highest end SMA connectors don't solder to the board; they get clamped onto it.
Oh, I was going to say press fit, but they're clamped.
Well, that press fits through a hole, right? With it, where you have a pin that is jammed into a hole, and it forces that metallurgical bond.
Right, it displaces.
But yeah, the equivalent to that with good RF SMAs is a clamp arrangement where the SMA is bolted to the board, but the center pin of the coaxial portion of the connector bites down in like a vampire into the microstrip trace.
Got it.
And those connectors can cost hundreds of dollars a piece.
Right. Are they reusable even? Probably not. So
I don't know. The connectors may actually be reusable 1 or 2 times. Obviously the PCB that it clamps onto isn't.
Right.
Once it's been bitten down into, that's it. Like you've deformed the copper and the trace plating. So, yeah.
Hey, not to put you on the spot, could you show a QAM?
I haven't.
Do you have a demo for QAM?
It does have one, and I tried to find it before, but real quick first before I show my ineptitude.
Right.
I want to see if I can. Come on, zoom in on this. This is the TDR response of the cable.
Oh, cool. Cool.
How do I get it to zoom in though?
Can you use 2 fingers and
I was trying that. Pinch? That didn't do it.
Yeah.
That didn't do it. I'm trying the zoom function.
We did not have this problem in the 1980s of interactive touchscreens not zooming the way you thought they should.
Yeah, that's true. What's this? This is the overall normalized, basically frequency response of that little piece of cable I inserted. So it's taking into consideration. Cool. So it's actually de-embedded the probe leads that came with the scope because they already had some loss, which we saw in our captured analysis before. So it subtracted that, and now it's showing more or less flat bandwidth all the way out to the 15 gigahertz. So these cables that came with the FPGA are actually not bad.
Right.
Not bad. I should put those aside because I know there's others I have that are absolutely janky.
Yeah, I have a whole carrying case for my SMA cables.
So I have some which are like a foot long, and they're semi-rigid. These are probably even lower loss, but these were cheap. So I'd say the cable itself is good, but the connectors are probably terrible.
Right. Yeah, my best cables here are probably 12 gig, just knowing what I buy for mini circuits. So, because I typically work up to 6 gig.
Right. And even that's pretty darn good. 6.
Oh, in the old days, it was like, oh, that's radar.
Yeah. Yeah, so if we go to RF, there is a constellation thing here. And I was looking at that before, but I went away from it because I couldn't figure out how to get it to actually show up. Because it's not guided like some of the other demos.
Right.
IQ sampling. Input type real. 20 gigasamples a second sample rate. Could do normal or inverse sidebands. See carrier frequency of let me type into there. Okay, this is where I have a little wireless keyboard I plugged in. I want to do something more chunky, like 100 megahertz. So this is channel 1, channel 2. I think I would have to have an external, I may have to have an external signal generator generating this first. Yeah, so I think that's just an input side thing. Wonder if they have something like that in demo though. Let's see. We've got frequency analysis, RF. Let's have a look in RF. So we started out with the spectrogram. What's pulse analysis? Yeah, we could try that one. Yeah, so it'll do a constellation, but I think I probably have to have an external modulated source for that one. I'm not sure. Or I could use the generator module, but I'd have to have a pre-sampled.
But you do your IQ sample or your IQ demo did that, right?
Well, it was setting up, I think, for decoding. I'm not seeing much there. That's not interesting. Okay. Let's see what else we got. Well, okay, what can we do with the generator?
Right, because all you need is a modulated signal, right? To demonstrate QAM, a phase modulated.
Yeah, I'm not sure if the generator can actually do that modulation though in this.
The constellation.
I need to read up on it. What's in Rody and Schwartz apps? Okay. There's some power electronic stuff in here too, so that's pretty cool.
Oh, does it calculate like phantom power, stuff like that?
I don't know. I haven't looked at it yet. So I'm just switching over the cable connections here to agree with what they're requesting for this. Oh, wait. This requires the... I need another BNC to SMA adapter. So give me a second. I've got to run and grab it.
All right. So clearly Ben's lost his ball off in the rough on the right side of the course. We haven't seen Ben in an hour and a half. We're going to be sending people in after him to try and locate him and the ball.
Well, golf course is about the only place I'd be willing to lose balls.
Ah.
Man, it's getting hot in here. This thing puts out a lot of heat. That's the thing. I like any powerful computers.
Right.
Like I've got my rendering workstation here running StreamYard. It's hot. Got this scope. It's hot.
So while you're doing that, I can relate. You were talking about power and things like that, and that made me think of dynamic switching times in CMOS, where your power draw is related to the frequency of your edges, right? How many, how often.
Right.
And I was just talking to Albert Charpentier, designer of the VIC chip. I had seen that he had a patent recently on MOSFET drivers. So I asked him about it earlier this week, and he talked about how they didn't use just a single RC to drive the gate. They used multiple steps of multiple values, so that and this is for GaN and high end MOSFETs, they actually shape the gate voltage presented to the gate to eliminate overshoot and to make up for that initial capacitive charge and stuff.
Oh, that's
so he's
cool.
got a dynamic gate driver that you just and it made perfect sense. It's like, why hadn't somebody done this before?
Because they didn't have to.
Yeah, part of it is the power stuff's getting big,
Yeah,
bigger.
Okay, so I've got my cables sorted here.
All right.
That reminds me of the
electronics.
And
that's cool.
Actually, there's more than that. There's a chip tunes. What's it called? It's people generating chip tunes that also create images and shapes on the oscilloscope. What's it called? It's a whole library.
I don't know that I've seen it.
I gotta find it real quick.
And you're talking about a library of signals that also make XY diagrams on their scopes.
That's right. It's is it oscilloscope
it's like
music?
Automatopoeia or some name like that.
Yeah, ASDFG, XXY.
Isn't
No,
that
there's
an
a few of them.
piercing, discarding Szabo round? Oh, never mind.
It's especially interesting to us though because it's perfect for chip tunes. It's I think this is the one. Let me share my screen, my other screen. Give me a second here. Yeah, Oski Studio. That's the one I was trying to think of. It's a program that's basically lets you put music and it's got a library of shapes and stuff, and so pre-captured waveforms.
Got it. Okay.
But the thing is, like, this pre-captured waveforms for doing line drawing, even 3D shapes like cubes and stuff that are animated. But the idea is you play them back. You can play them back at a certain frequency.
Right.
And so you can assign them to notes and then put a MIDI file in, and you can play your chip music and generate fancy oscillograms to go with it.
Right. Does
Like
your scope do MIDI? I was looking while we were.
It would. I don't know if it's got a built-in MIDI protocol analyzer. I doubt it.
That's what I meant. Yeah.
I doubt it has that, because the appeal of that would be pretty limited.
Would be small. Yeah, I realize it's kind of like, well, it's old technology.
See what it does have though, like protocol. It's I2C, SPI, UART, all the ones you need for a serious industrial designer there.
1553.
Yep. A-Rink. Yeah, I'm not seeing MIDI. You could add it though, because here's the thing: you can go to user apps and you can actually create your own. So
yeah, I see the math symbol there.
This one?
Yeah.
Let's have a look at this. It's got all, so DDT, logarithms, integrals, rescaling. I feel like that menu goes off the bottom, but I can't scroll any further. Yeah, so let's take channel 1 and we'll do DDT on it. Or we could filter it with a low pass, or we could do FFT. Or we could do a custom equation. So you could, pretty much put any function in there.
Yeah, that's cool. You can MATLAB it.
Yep. And I think even then, once you've set things up like that, you can trigger from them. If we look at triggering, you can
right
trigger on a sequence. So it's got traditional trigger. But you could actually basically say, look at this. You can specify there's some built-in sequences there. A, then B, then R. And you can choose.
Frank Buss just mentioned MIDI is just 8-in-1 with 31250 baud.
Yeah, and you would, so I guess technically then yes, it does have that, because you'd go use the UART, this one. You'd use UART, and then you'd set that. The bit rate would be 31.25 kilobits per second.
Right.
8-in-1. No parity. It's true. And really, it's MIDI is really almost like 7 bits, but it's 8, because the most significant bit says is this a regular command or is this system exclusive or something like that. Yeah.
Cool. Well, it's past the hour, but this is very cool.
Yeah. We'll show more of this in the coming, few weeks, I guess, as I learn more about it and do some more interesting things with it.
Yeah.
We can have a look at that.
Would we be able to actually, do you think we could get into something with DDR3 or DDR4 and see it?
That's the goal, but to actually connect and probe in will be tricky.
Yeah.
Need to find or obtain somehow the right kind of probe tips or an interposer or something. So I don't know yet how that's going to work. USB 3 might be a bit easier.
USB is the other one. Yeah.
Yeah, or even USB 2 is still It's still
Yeah.
half a gigabit per second. It's still pretty fast.
Right.
But yeah, I mean, that's the idea. So
Cool.
cool.
All right. Well, Ben, this was fantastic, and as you said, let's do this some more in the future as we find cool things to play with in the scope.
Yep.
You want to do a pitch for Coriolis?
Yeah. Join the Discord.
Yeah, there you go. Where can they find the Discord?
Let me throw a banner up and you'll see.
Yeah.
If you go to this website Bill put up for, it's basically a proxy to the YouTube channel and all these streams
That's
that we
right.
do. But if you go to the top, there is a link that says Discord, and you can join our Discord. There's a pretty thriving community there now. Actually, quite a few people, lots of discussion.
In real time. Yeah.
Yep.
We've had a couple Saturday nights where we've had a live event, kind of like a roundtable event of people from the Discord channel joining and showing different stuff. So yeah, join our Discord.
Definitely. It's fun.
And while you're at it, throw a like at this video. I'm told we should ask for likes, more subscriptions. Don't throw a like on this. I do not want you to like this video.
Well, either way, Bill, it's your channel, and you didn't monetize it or anything.
No, I turned it on as an experiment. Made $5 and I turned it back off.
Yeah, I mean, so we largely do this for the passion of it. It's not, obviously we don't make anything for it, but we just wanted to join people together who have common interests. So
right. And so as you know, my computer reset right in the middle of the broadcast today. This is sitting there waiting to go into it just to rule out that it's the power, because it didn't blue screen or anything. It just went click and was off.
Yeah, that seems like a power supply problem to me.
Yeah. I mean, click and it was off. So cool. All right, we will see you around. I'll tell you offline. I may have somebody lined up for the next week or two, and we can talk about that more in the Discord.
Yep. Cool.
All right.
Good to see you guys.
And thanks for coming and viewing us today.
All right. Ciao. Enjoy your weekend.